So this is field due to a circular loop or a circular coil. That is the loop. And you can see the axis drawn there. And you can imagine that, well, so the magnetic field there is dB. And you know that that magnetic field can be, it's according to Byerton-Sauert's law, it's given by mu naught by 4 pi I dl sine theta by r squared. That is Byerton-Sauert's law. Okay, I just want to ask you, what are the terms? What's dl there? D, that's the length of that tiny section on top. R, which is r now. R is actually this distance, isn't it? The distance of the section from the point, that is R. What's theta? I is the current flowing through the loop, of course, and what is theta? That is very important. What is theta? How much is theta?
Isn't that the angle that the magnetic field is to the...
Yeah, how much is theta in this case?
In this case it would be 90.
How did you get that as 90?
Because
If theta is 90, then the whole equation changes. It becomes simple because sine 90 is 1, and the formula becomes dB is mu naught by 4 pi I dl by r squared. Now, that dB can be resolved into two components, and I've taken that angle as phi or phi, and you can resolve it into two components. One would be dB sine phi. The vertical component would be dB cos phi. I want to stop there. dB sine phi and dB cos phi. Now, diametrically opposite to the section that we considered, I'm talking about this section now here. Wouldn't there be a section diametrically opposite to the top section, the one right down at the bottom? That section would produce a magnetic field at that point P, which would be in the direction that I have shown. Look at that. Because that one is down there, it has to be perpendicular to the line joining, and so you would get it as that direction. Again, you could resolve that one into two components, which you're going to see. You can see the two components there. I'm talking about AB and CD now. And which of the components cancel out? The vertical, you can see that the vertical components cancel out. The vertical components, dB cos phi's, get cancelled, and you have dB sin phi's adding up. So to find the total magnetic field, already you know that the total magnetic field at that point P is along the horizontal, along the axis. That must be very clear because there's only dB sin phi. And so to find the total magnetic field, what you got to do is integrate. Integral dB sin phi. Now the rest of it is math. And we know that dB is mu naught by 4 pi I dl by r squared, so I'm going to substitute that. And then find sin phi from that right angle triangle that you find. It's A by R. Now I mark A is the radius of the loop. R is, there's R twice there, but you know what I mean. R, and X is the distance of the point from the center of the loop. So from the geometry, you know that sin phi is actually A by R. Of course, opposite side by hypotenuse, sin phi is A by R. Is that right? Plug it back into the equation and you get this. So this whole thing is there, and then R squared and R become R cube. So you have mu naught by 4 pi A by R cube, all constants taken out. The only variable is the length. Integral dl will give you the circumference, isn't it? So that will be 2 pi. 2 pi what? Nobody is with me? What is the circumference of the loop?
It is 2 pi A.
2 pi A. That's why I'm saying understanding is very important. Otherwise you have a whole bunch of letters there. It's 2 pi times A, and then do the simple math, cancel the pi's, take out the, then you have a squared by r cubed. Okay, one more thing. Is r a constant or a variable? Let me see how you visualized. Let me see how you visualize the loop. Remember, the loop is this way. The loop is this way and the point is here. So no matter what section you join to that point, r is a constant. R is a constant there. Okay. Now a is a constant too. Of course, a is the radius of the loop. And the only variable is x, which is not yet in the picture. Do you see that? It's not in the equation yet. So we're trying to bring x into the equation. And you know that r squared is a squared plus x squared, isn't it? And so r would be a squared plus x squared whole raised to half, which is square root of that. So take that and plug it back in here. For r cubed, you would get a squared plus x squared whole raised to 3 by 2, wouldn't you? So that'll be our last final formula. But I want to tell you that this is the magnetic field set up by a loop. A loop has only one turn. I mean, that's the meaning of a loop. What if there were n turns here? Yeah, because the current through all the n turns will be flowing in the same direction, isn't it? It goes back and back. So you'll have to multiply this with n, which I forgot right here. So your final formula should have an n here in the numerator. And that's a very important formula. That is the formula for magnetic field due to a current carrying coil now. Remember, A is the radius of the coil, I is the current that flows through it, N would be the number of turns, X is the distance of that point right from the center of the loop. X is the distance. So now let me ask you to do this. From this equation, can you find the magnetic field right at the center of the loop or of the coil? Yeah, what happens to X there? What's the value of X? X becomes 0. So you just put X is equal to 0, you get another equation which will be the magnetic field right at the center. So do that. And so at the center, X is 0. If X is 0, what happens here is this whole thing vanishes and a squared raised to 3 by 2 would become a cube, right? A cube. And then a cube and a squared will get cancelled and you will have 2a in the denominator, right? That's it. So that would be the final formula. For n terms, b is mu naught ni by 2a. I think it's on the formula chart and that you got to remember that. If it's not there, that's very important, crucial.
This is for the one at the center. So it's going to go like this.
At this rate, to do 5 problems, we would take 5 hours. Anyway, but still, it'll be fine. This is the diagram that's been given. Call that angle theta 1, this angle is theta 2. Let's slow this down. And I need your total concentration. You see those two red vectors? Those are the magnetic fields produced by the 2 wires.
Yeah.
And, okay, this one, this is the magnetic field by which one? Which conductor?
This one. The bottom one.
It's by this conductor. I mean, because it's perpendicular to the plane. Okay, and this one
Well, yeah.
is the magnetic field produced by bottom. Well, if you're not able to get that, you got it? Easy. It becomes easier now.
I need to just find the map. No?
And geometrically, will those angles be the same? Theta 1 and theta 2? Well, 13, 10, and I'm just trying to label all that. I didn't have space there, so I put it as theta 2 there. B1, what's the formula for magnetic field? By a straight conductor. E naught by 2 pi? I by R, isn't it? Okay. So you calculate that, put that in. 4 pi times 10 to the negative 7 times the current carried is 35 divided by 2 pi times the distance is 6 centimeter, which is 0.06. And when you calculate, you should get 1.17 times 10 to the negative 4 Tesla. You see, I'm trying to use the time which you would have swallowed for calculation to explain. You see what I'm doing? So forget about calculating and getting that. Just go with me. You got it. All right? Okay. Can you write down the formula for B2 now and plug in the numbers?
Yes.
Go on. B2 is equal to? V naught by 2 pi. What is right? Not go with the solutions. Close that, please. Close it. That's for you to use at home. Now try to write.
I mean,
You said this is right. Okay.
Why don't we use 106 for B1?
Because what's the distance? That's why I said B1 is the magnetic field produced by which conductor, the top or the bottom? The top. And the distance from the top to that point is 6 centimeters. Isn't it, Steph? And so for B2, you would use 10 centimeter, 0.1 meter. Okay. So B2 would be mu naught I by 2 pi r, R2, whatever. Okay, so that's equal to, substitute the numbers, and you should get 7 times 10 to the negative 5 Tesla. I hope it was that easy. Okay, using the cosine law, this is what you should have written. 0.06, I changed it to meter. 0.06 squared plus this, minus 0.1 squared divided by 2 times 0.06 times 0.13. And you said 47.7 degrees. Okay. 0.6 something, isn't it? Yeah, 47.7. All right, so if you can get that, you can get the other angle too. Here is theta 2 for you. Theta 2 is cos inverse of the same process. Because this time you take 0.1 squared plus 0.13 squared minus 0.06 squared, isn't it? Divided by 2 times 0.13 times 0.10. That gives you 26.3 degrees. So you got your theta 1, you got your theta 2. Okay, Bx is B1 cos theta 1 minus, remember the x components are opposite, so right, B1 cos theta 1 minus B2 cos theta 2. You plug in the numbers. 1.174 cos of 47, what you got, minus, do the same thing. You calculated B1, B2, remember, put in the numbers there, and you calculate it to be 1.626 times 10 to the negative 5 Tesla. Now you do the same with the y component, but remember that the y components add up, isn't it?
Yes, you just add.
Okay, add them up. So you can expect one of these questions in the exam, and it should carry like 10 points if it's asked, and it would surely be.
Is this multiple choice?
This is not multiple choice.
No,
It's going to the test would be multiple choice, but you would always have some questions tagged on at the end like this. So the process of guessing throughout is taken away. So it will be a mix of both. All right, so you get B1 sine theta 1 plus B2 sine theta 2. Add them up like before, and you would get 1.18 times 10 to the negative 4 Tesla. What do you do next? Yes, square root of both squares, yes. Okay. Okay, you were. So square root of that, bx squared plus by squared, and you get your answer. 1.19 times 10 to the negative 4 Tesla. And theta, you can find theta also. That is the angle made by the resultant. This way, it's the angle made with the x-axis. Tan inverse by bx would give you 82.2 degrees. With the horizontal. Okay, here it is. Here it is. This will make it more clear. Okay, BW is the magnetic field due to the conductor, and then BE is the magnetic field due to the earth. Isn't it? Okay. See, why was it that way? Because, look, at this point, it has to be tangential to the circle. Isn't it? It has to be tangential to the circle, isn't it? In circular loops, magnetic field is in circular loops, but tangential to the circle at that point. So you have one going straight up, that's the magnetic field due to the conductor, and then you have this, the earth. All you have to do now is find the resultant of the two, for which you have to break it up into two components. But it's so good here, easier, because this has no x component. Does it have an x component? No. So the only thing that you have to break up is the Earth's magnetic field into x and y, which I'm doing here. So, all right, the magnetic field due to the conductor is given by this formula, mu naught I by 2 pi times r, again, and the current is 24, the distance is 0.2, 2 pi times 0.2, which is 20 centimeter. That gives you 2.40 times 10 to the negative 5 Tesla.
Can you draw the point? The point 20 centimeters away?
That's the point where you see all the vectors meeting together.
Okay.
Isn't it?
That's what I was thinking.
Okay, that's the point. Where you have all the three vectors meeting together. And then the Earth's magnetic field is given here as 5 times 10 to the negative 5. And it's 44 degrees below. So when you resolve that into x and y, you would get BE cos 44, which gives you 3.6 times 10 to the negative 5. And then the y component, because the other one is totally the y, isn't it? So you'll have to subtract. I hope you understood why you have to subtract. If you see that picture, you see that it's broken up. The y component will be down. So that's why the understanding is so important. And then the net will be as before, square root of the squares of both of them. And that's your answer. Okay. So this is the final answer, 3.8 times 10 to the negative 5. Again, theta, which is the angle by the resultant, would be this angle there, is tan inverse by bx, tan inverse of the components that you got. Divide and get the angle as 17 degrees. And of course, it's going to be below the horizontal, as you can see in the diagram, isn't it? Is it below the horizontal? 17 degrees below the horizontal. That's the way to do it. And this is okay. For if you found it a little bit difficult, then here it is for you. The magnetic fields are opposite to each other because they cancel out, and it says it's 0. So surely they must be opposite. And the net magnetic field would be one minus the other, isn't it? Set it equal to 0. That's why I said if you could think about all this math in your head, you can just directly set them equal to each other.
Yeah, I just didn't know.
Yeah. Directly set it equal to each other. See, I was trying to follow the solutions manual in case if you look at it, and I try to use the same angles, the same letters, so that you don't get confused. Because I know this thing is all over the place now. So rearrange and find I2. I2 is I1 times R2 by R1. Definitely you know that the other distance would be 6, take away 2.2, isn't it? Because that's the distance from the other conductor. 6 take away 2.2, and you get it as 3.5 amps. Problem done in 3 minutes. All right, I try to draw it this way now. Does this make any kind of sense?
Yes, it's a resultant.
Yeah, either one, yeah.
Okay.
The magnetic field due to the Earth, the magnetic field due to the... How did I know that the magnetic field due to the conductor should be... I've been saying it should be tangential, it's a circular loop, and the reason I know it's downwards is because what was at 20... How much was it?
Yeah,
28, suddenly dropped to what? 55.
Yeah.
So the Earth's magnetic field was 28 down. Now suddenly it's gone to 55, which means the magnetic field due to the conductor was pushing it further down, right? So it was towards the south. Okay. And that's the net magnetic field now.
Can we find it?
Wait, where do we
Torque?
So you have several angles which you have to again find out in this problem. You have to find theta, phi, and beta. Those triangle, inside the triangle, simple thing, theta is 28 degrees given, theta plus phi is 55, so phi should be 27. And then put those two there, you would get, because all of them should add up to 180 degrees. Total angle in a triangle is 180. So you get beta as 180 minus 55, which is 125. Okay, now we have to use the law of sines. Okay, what's the law of sine?
It says that the side of across from one angle over that angle is proportional to the...
Perfectly, exactly. Okay, so in this triangle, how would the sine law work out?
Looks like...
It would be sine B divided by AC. You see that?
Yeah.
Sine of the angle divided by the side opposite is equal to sine C divided by AB is equal to sine A divided by BC. I'll try to say that one more time. Take sine of the angle, sine of A divided by the opposite side is equal to sine of B divided by the opposite side is equal to sine C divided by the opposite. So the ratio of the sine of the angle to the opposite side is the constant. So we're going to use that there. So you would have magnetic field due to the conductor divided by sine phi, because that's the opposite angle, is equal to, we're only taking two ratios here, BE by sine beta. Use that to find the magnetic field due to the conductor. But we also know that the magnetic field due to the conductor is given by this formula, isn't it? Mu naught by 2 pi I by R. So you set that equal to this whole thing. So that solve that for the current, make I the subject, you know everything else. Plug in the numbers. You get the current. Mu naught is 4 pi times 10 to the negative 7. We've written that like 10 times now, isn't it? And it always crosses out with the pi on top. It'll always have mu naught by 2 pi, either mu naught by 4 pi in every formula, so it becomes easier. So it's 17 ampere, and we know it's flowing down because of what I explained to you before, because pushed that down from 28 to 55.